This is part 3 of the tutorial on theory and application of energy-based generative models. In this part, we will talk about applications of 3 types of energy-based generative frameworks. The first one is the energy-based generative neural networks, which is an energy-based model with the energy function parameterized by modern neural network. The second one is the energy-based generative cooperative network, which is an energy-based framework that jointly trains an EBM and a generator by MCMC teaching. The last one is the latent space energy-based model, in which the EBM is built on top of a top-down generator. I will first talk about the applications of energy-based generative models on image domain. Learning energy-based generative models for image synthesis has been very successful. Here, we show some image generation results sampled from the energy-based models by using long-train dynamics. The learned models can generate realistic texture, face, and scene patterns. The energy-based model can also be useful for image in-painting. Once the model is trained on fully observed training examples, given a test image with a mask occluding some pixels, we can use the long-range sampling initialized with that occluded image to recover those missing pixels. In this figure, we can see that the model is very creative to in-paint diverse and reasonable patterns for each occluded image. In this example, the model is trained by a multi-stage cost-to-fine expanding and sampling strategy. It means that we gradually expand the resolution of the energy function such that the training and sampling can be more stable. As to unpaired image-to-image translation, people might recall CycleGAN, which trains 2 adversarial frameworks with cycle consistency. Here, I want to show you how to use energy-based model for this purpose. We can easily train a single energy-based model for one-sided image translation. For example, given 2 collections of images representing 2 different domains, the examples of these 2 datasets are unpaired. So this is an unsupervised image translation problem. What we need to do is to train an energy-based model on the target domain. During training, we need to initialize the short-run MCMC with random sample from source domain at each iteration. Once the training is done, the short-run MCMC will serve as a flow generator that maps the example from the source domain to the target domain. This method is simple and natural. No explicit cycle consistency loss is needed. Now let's move to the video domain. The Spatial-Temporal Generative ConvNet is an energy-based generative framework defined on video. It generalized the generative ConvNet by using Spatial-Temporal ConvNet to parameterize the bottom-up energy function, which is helpful to capture spatial-temporal information from videos. The model is in the form of exponential tilting of a Gaussian reference distribution and trained by analysis by synthesis. Long-range dynamics is used to draw samples from the distribution. I will show that later. Different design of the function f in the model can represent different types of video patterns. Dynamic textures or texture motions exhibit statistical stationarity or stochastic repetitiveness in the temporal dimension. Examples of dynamic textures include flowing water, spatial-temporal filters that are convolutional in both spatial and temporal domains can be used to design the energy function f. Here, we have some synthesis examples generated by the energy-based model that used 3 layers of spatial-temporal convolutions with nonlinearity and subsampling. For each example, the first one shows the observed video, and the rest 2 are generated by long-range sampling from the learned model. Many dynamic textures have structured background and objects that are not stationary in the spatial domain. For example, a video exhibiting burning fire hitting a pot. In this scenario, we need to modify the level F in the last case by using filters that are fully connective in the spatial domain at the second layer to account for spatial non-homogeneity of the dynamic textures. Qualitative synthesis results are displayed in this figure. The energy-based spatial-temporal generative ConvNet can learn from videos with occluded pixels. This task corresponds to unsupervised video in-painting or recovery. Since in the training stage, the model doesn't have fully observed training data, the learning algorithm of the energy-based model for complete data can be adapted to this application with minimal modification. The modification is that for each iteration, we run a few steps of long-range dynamics to recover the occluded regions of the training example. The additional long-range dynamics for recovery is initialized by the observed occluded example, and it only synthesizes the occluded regions while keeping the visible paths unchanged. At each iteration, we use the recovered observed example and the synthesized examples to compute the gradient of the log likelihood and update the model parameters. The algorithm simultaneously accomplishes 3 tasks. The first one is recover the training data. The second one is synthesize new video examples. And the third one is learn the model parameters. Here are some recovery results by learning energy-based spatial-temporal generative ConvNet from incomplete data. There are 3 types of masks for occlusion: salt and pepper masks, mixing frames, and single region masks. Here, I want to emphasize that the model we show is different from the denoising autoencoder. In the denoising autoencoder, the training data are fully observed, and noises are added as a matter of regularization. It also differs from supervised denoising or supervised in-painting, where the prime model has already been learned from fully observed data. Also, learning from incomplete data can be difficult for GAN and VAE. Now let's talk about an interesting application of this learning while recovery algorithm. If a moving object in the video is occluded in each frame, it turns out that the recovery algorithm will become an algorithm for background in-painting of video, where the goal is to remove the undesired moving object from the video. Here, we saw 2 examples of background in-painting by energy-based generative models. Now, let's talk about the application on 3D computer vision. We will first focus on voxel representation and then point cloud representation. Energy-based generative VoxelNet is an energy-based framework for 3D volumetric shape representation. It parameterizes the energy function by a bottom-up 3D convolutional neural network structure and follows the same modeling and learning scheme of the generative ConvNet model. This model is powerful for 3D volumetric shape generation and outperforms GAN-based and VAE-based methods in terms of inception score, which is a measure to quantify the synthesis quality. To generate high-resolution 3D shapes, the model can be trained more efficiently by multi-grid modeling and sampling strategy. We can learn a pyramid of energy-based generative VoxelNet. Each of them accounts for one resolution. Each scale of model is trained against the training example at its corresponding resolution. The pyramid of training examples at different resolutions can be obtained by downsampling the original example. The benefits of the multi-grid modeling is that during training, the low-resolution EBM can provide initialization for the MCMC of the high-resolution EBM. Usually, sampling from low-resolution space is much easier than sampling from high-resolution space. The starting minimal resolution is typically 1 by 1 by 1, and the largest resolution is the target resolution. Here are some results of generating 3D volumetric shapes by multi-grid modeling and sampling. The target resolution is 128 by 128 by 128. Sim-size example at each grid is obtained by 20 steps of long-range sampling, initialized from the sim-size examples at the previous cursor grid, starting from the 1 by 1 by 1 grid. Different scales of sim-size along the multi-grid sampling process are also displayed. "3D shape recovery" is another interesting application of the generative VoxelNet. Given a corrupted 3D shape with known voxel positions of the corruption, the goal is to recover the corrupted voxel. Here, I'm going to introduce a self-supervised method to achieve this goal. Given a data set of 3D shapes, we can easily generate a corrupted versions of dataset by randomly masking some voxels of each 3D shape. Then we learn a distribution of invisible voxels conditioned on visible voxels. Such a conditional distribution can be used for inpainting. The model is trained by analysis by sim-size scheme, where the sampling from the conditional distribution is achieved by starting from the corrupted example and then run a few steps of long-range dynamics to obtain a sim-size example. We fix those visible parts and only update the corrupted regions. The recovered examples are used to compute the gradient of the log likelihood to update the model parameters. Here are some results of 3D shape recovery for each category. The first row shows the original examples, and the second row shows the corrupted testing examples. The last row shows the recovered result by the learned model. The recovery is performed by running a few steps of long-range sampling, starting from the corrupted examples. Similar strategy can also be applied to 3D super resolution, which seeks to increase the resolution of a testing 3D object. A low-resolution 3D dataset can be easily created by downsampling a higher resolution dataset. Then a distribution of high-resolution 3D shape conditioned on the corresponding low-resolution 3D shape is trained for super resolution. The idea is similar to the one in the recovery application, except that the sampling from the conditional distributions are different. For sampling, it first upscales the low-resolution example by expanding each voxel into a D by D by D blocks. Here D is the scaling ratio. of constant intensity to obtain an upscale version of the low resolution example. And then it runs long-range dynamics starting from the upscale versions to obtain the high resolution output. Super resolution results for category, toilet, and sofa are shown in the figure. The energy-based generative VoxelNet can be useful for classification. We need to first train a single model from all categories in an analysis by synthesis manner. The learned bottom-up network can be treated as a feature extractor. We can learn a multinomial logistic regression classifier from the labeled data based on the extracted feature vectors for classification. The table on your right-hand side shows a comparison among different baselines for 3D shape classification. Point cloud is another important data format to represent 3D objects. It is a standard 3D acquisition format used by devices like LiDAR on autonomous vehicles, Kinect for Xbox, and face identification sensor on phone. Compared with voxel representation, point clouds can provide a compact and detailed representations of a 3D object. Learning a generative model of 3D point clouds for point cloud generation, reconstruction, and classification is a fundamental problem for 3D computer vision. A major challenge in modeling 3D point cloud is that, unlike images, videos, and volumetric shapes, point clouds are not regular structures, but unordered point sets, which makes extending existing energy-based paradigm intended for structured data not straightforward. Energy-based generative PointNet is an energy-based model for unordered point clouds, with the energy function parameterized by a well-designed input permutation invariant bottom-up network. The MLE training of the model follows analysis by synthesis scheme. The input permutation invariant bottom-up network F first takes all unordered points as input, encodes each point into features by multilayer perceptron (MLP), and then aggregates all point features to a global feature by average pooling, and eventually output a scalar by another MLP. This figure shows some 3D point cloud synthesis generated by the learned energy-based model by short-run MCMC. Since the model is trained with k-step short-run and non-convergent MCMC, the sampled point cloud X is highly dependent to its initialization Z. Therefore, the short-run MCMC process can be regarded as a k-layer flow-based generator or a latent variable model with the initial point Z as the continuous latent variable. We can use this latent variable model for reconstruction purpose. To be specific, given a new testing point cloud, we find the latent Z of the short-run MCMC generator to minimize the reconstruction error. The figure shows the performance of reconstruction. The second row displays the result of the energy-based generative PointNet. The third row displays a baseline point flow. Since the short-run MCMC is a latent variable model, we can also perform interpolation in the latent space to demonstrate that the learned latent space is meaningful. Here are some examples. The transition in each row displays the sequence of reconstruction with the linear interpolated latent variable Z. The learned point encoder in the score function can be useful for point cloud feature extraction, and the features can be applied to supervised learning. We first train a single generative PointNet on the training examples from all categories. We then replace the average pooling by a max pooling layer in the learned score function, and use the output of the max pooling as point cloud features. Such a point cloud feature extractor is also input permutation invariant. An SVM classifier can be trained from label data based on the extracted features for classification. The table shows the classification accuracy using the 1 versus all rule. The 3 curves show some robustness test, considering 3 types of data corruptions. Type 1 is missing points, where we randomly delete points from each point cloud. Type 2 is added points, where we add actual points that are uniformly distributed into each point cloud. Type 3 is point perturbation, where we perturb each point of each point cloud by adding a Gaussian noise. We report classification accuracy of the classifier on the corrupted version of point cloud data. The performance decreases as the corruption level increases. In the case of missing point corruption, even though 94% points are deleted in each example, the classifier can still perform with an accuracy 90.20%. In the extreme case, where we only keep 20 points in each point cloud, the accuracy becomes 53.19%. In this section, we will talk about energy-based continuous inverse optimal control and trajectory prediction. The problem of continuous inverse optimal control is to learn the unknown cost function from expert demonstration. This problem can be studied in the framework of energy-based model, where the observed expert trajectories are assumed to be random samples from the probability density function, which is defined as the exponential of the negative cost function up to a normalizing constant. In particular, we talk about the control problem of finite time horizon, where the trajectory is over a finite period of time. We will focus on the problem of autonomous driving as a concrete example. Let xt be the state at time t. The state might include longitude, latitude, speed, heading angle, acceleration, steering angle. Let's use ut be the continuous control or action at time t. The control might include the change of acceleration, change of steering angle. The dynamics f is known. We use both t and both u to represent time sequences of state and control respectively. The trajectory is the pair of both x, u. The cost function with learnable parameter is defined on the trajectory and some history and environment conditions. The problem of the inverse optimal control is to learn the parameters of the cost function from expert demonstration D. The distribution of control conditioned on the history and the environment can be represented by an energy-based model, with the cost function serving as the energy function. States X can be determined by the control U according to the dynamic function. As to the demonstration, control U are assumed to be sampled from the distribution, so that U tends to have low cost The parameters of the cost function are learned by maximum likelihood by analysis by synthesis scheme. For the synthesis step, the trajectory of x and u can be sampled by long-term dynamics or predicted by optimization methods that directly minimize the cost function. Once the cost function is learned, trajectory prediction can be performed by long-term sampling from the conditional distribution. Here are some example results of the trajectory prediction. The red dot represents the ground truth trajectory, and the green dot and the blue dot represent the result obtained by energy-based framework and GALE, which is GAN-based baseline. The energy-based framework can be generalized to the multi-agent scenario, where there are k agents, and each agent has a trajectory. In this case, we simultaneously control all vehicles in the scene. The overall cost function is said to be sum of each agent. The prediction is still performed by long-range sampling from the learned energy-based model. In this section, we will move to energy-based framework for internal learning. Different from external learning, where the goal is to learn the distribution of a dataset, the internal learning seeks to learn a distribution of patches within a single natural image rather than relying on external data. The Patchwise Generative ConvNet is an energy-based framework for internal learning. It trains a pyramid of EBMs and trains against a pyramid images of different scales. Each EBM is trained by analysis by synthesis and is responsible to generate images based on the patch distribution learned from the images at the corresponding scale. A cost-to-find sequential training and sampling strategy is used to train the model efficiently. Specifically, the sampling process starts from a randomly initialized noise image with the minimum scale. For each scale, the initial synthesis is updated by k steps of long-range revision, except that the initial synthesis at the minimum scale is from uniform distribution. The long-range dynamics of any other scale is initialized from the upsample version of the long-range output at its previous scale. The left figure displays some results of unconditioned image generation. Each row demonstrates a single training example and multiple synthesis results of various aspect ratios. The framework is able to generate realistic images with arbitrary size and aspect ratios by sampling from the learned distribution that capture different scales of internal statistical properties of patches within the input image. The right figure shows the influence of the numbers of scales that we use in the model. Given a single image, can we learn to increase its resolution without relying on external data? The Patchwise Generative ConvNet can perform this task. We first learn a model on this single image. After the pyramid of EBMs is learned, only the largest scale of EBM will be used to increase the resolution of the original image. The resolution of the original image can be increased by multiple times of expansion. Each expansion includes an upsampling operation and MCMC revision by the largest scale of EBM. This figure shows some example results of single-image super resolution. Given a background image, we can manipulate it by either copying and moving some region or pasting an external object in it. The Patchwise Generative ConvNet can blend the pasted object with the original background image or smooth the artifacts due to editing. We first train the model on this background image and obtain a pyramid of EBMs. We then create the downsample version of the edited image. We then use the pyramid of the learned EBMs to perform the multi-scale sequential sampling, starting from the downsampled version of the edited image. The multi-scale MCMC revision can smooth the artifact of the edited image by minimizing the energy function at different scales. Here are some examples. The top example shows that the model can blend the original image with an external object by preserving the object's identity and applying the learned texture and color information to the object. The left example shows that if the edited image is a painting that specifies the layout of semantic object, then the resulting synthesis will be an image in which the global structure of the painting is preserved, while the texture matching the background image. The right example shows that the method can remove the artifact of the edited image where some region of the image is edited. Now let's start to talk about another type of energy-based framework, the generative cooperative network. The energy-based generative cooperative network have been very successful in unconditioned image, video, and 3D shape generation. Now we want to focus on supervised conditional learning. Just a little bit notation. Let X be the D-dimensional output signal of the target domain, and C be the input signal of the source domain. C defines the problem, and X is the solution. The goal of the conditional learning is to learn a conditional distribution P of X given C, which is the distribution of the target signal given the source signal, or the distribution of solution given the problem. Examples of conditional learning include label-to-image synthesis, image-to-image synthesis, and supervised image in painting. The unconditioned cooperative learning scheme can be easily extended to the conditional learning problem by jointly training a conditional energy-based model and a conditional generator model. Both two conditional models represent the problem and solution from two different perspectives. The conditional energy-based model learns an objective function in the form of a conditional energy function, so that the output can be generated by optimizing the objective function, or more rigorously, by sampling from the conditional energy-based model. This corresponds to slow thinking, because the sampling is accomplished by an iterative algorithm, such as long-chain dynamics. The conditional generator generates the output directly by a nonlinear transformation of the input and the noise vector, where the noise vector accounts for uncertainty. This amounts to fast thinking, because the conditional generation is accomplished by direct mapping. The two conditional models are trained jointly in a cooperative manner, where the conditional generator serves to initialize the sampling process of the conditional energy-based model. while the conditional energy-based model refines the initial solution by an iterative algorithm. We call the conditional generator the fast-thinking initializer, and the conditional energy-based model the slow-thinking solver. The solver learns from the difference between the refined solution and the observed solution, while the initializer learns from the difference between the initial solution and the refined solution. Here are some examples of image generation conditioned on class level. The figure on your right-hand side displays the top-down level that we used for the conditional generator and the bottom-up level that we used for the energy function. Here are some examples for supervised image-to-image generation by the Learn Generative Cooperative network. In this section, we will talk about unsupervised image-to-image translation. Unsupervised cross-domain translation is more applicable than supervised cross-domain translation because supervised image-to-image translation relies on paired training examples between two domains. However, manually pairing up examples between two domains is costly in both time and efforts, and in some cases, it is even impossible. For example, learning to translate a photo to Van Gogh-style painting requires plenty of real scene photo paired with their corresponding paintings for training. Now, we will introduce an energy-based framework which is the cycle-consistent cooperative network for unsupervised image-to-image translation. Suppose we have two image collections from domains X and Y, respectively. The examples of these two sets are unpaired. The cycle-consistent cooperative network simultaneously learned and aligned two cooperative networks. Each contains an EBM and a generator for one direction of translation. We take the direction from Y to X as an example. The generator G from Y to X, parameterized by an encoder-decoder, maps example from source domain Y to the target domain X. While the energy-based model P of X further refines the mapped result by long-range dynamics, such that the revised results match to the examples in the target domain in terms of statistical properties. The other pair accounts for the other direction of translation. Two directions of mapping are aligned by enforcing mutual invertibility on the two generators. Now, we are going to talk about the learning algorithm of cycle-consistent cooperative network. The algorithm is called alternating MCMC teaching, which iterates the following three steps. First, cross-domain mapping. Secondly, density shifting. Third, mapping shifting with cycle consistency. In step 1, which is cross-domain mapping, for each domain, we randomly sample some training images and use the generator, which is an encoder-decoder structure, to map them to the other domain. The output of the generator is revised by a few steps of MCMC of the EBM in the other domain. This means that those translated examples will be sent to the local modes of the EBMs. The generators are visualized as arrows in this figure, with red color indicating a mapping from domain Y to X, and blue color indicating a mapping from domain X to Y. We will use X and Y to represent training data, X hat and Y hat to represent outputs by the generators, and X tilde and Y tilde to represent the outputs of the MCMC by the EBMs. In step 2, given the refined sequences X tilde and Y tilde and the observed data, the EBMs can update their parameters, which is equivalent to shifting the EBM density toward the data distribution. Step 3 is about how to update the translator or generator G. Each translator G is trained with MCMC teaching laws, which means they shift their mapping to the EBMs. We also align these two mappings by enforcing GY to X and GX to Y to be inverse functions of each other. This amounts to adding a cycle consistency loss in practice. Here are some results of unpaired image-to-image translation by the cycle-consistent generative cooperative network. Results shown on your left-hand side are style transfer from photorealistic image to artistic style. The result displayed on your right-hand side are season transfer between summer and winter. Next, I'm going to talk about unsupervised sequence-to-sequence translation. We can generalize the cycle-consistent cooperative network to learning a translator between two domains of sequences, where paired examples are unavailable. For example, given an image sequence of Donald Trump's speech, we can translate it to an image sequence of Obama, where the appearance of Donald Trump is transferred to Obama, but the speech is in Donald Trump's style. In order to adapt the original cycle-consistent cooperative network to image sequence translation, we learn an actual recurrent model in each domain to predict future image frame given the past image frames in a sequence. We use Rx and Ry to denote recurrent models for domain X and Y, respectively. Each recurrent model is trained to minimize the output reconstruction error. With the recurrent models, we modify the cycle consistency loss of the generator G to take into account spatial-temporal information, and we call that the spatial-temporal cycle consistency loss. The final loss for training generator G and the recurrent model R is a sum of the recurrent loss, the spatial-temporal cycle consistency loss, as well as the MCMC teaching loss. Here, we show some qualitative results of unsupervised sequence-to-sequence translation. In the first example, we translate Obama's facial motion to Donald Trump. In the second example, we translate the blooming of a violet flower to a zero flower. In the third one, we translate the blooming of a purple flower to a red one.
Okay, we now come to the applications of latent space energy-based prior model. Just to remind you a little bit, so X is observed example and Z is a latent vector, and we learn a latent space energy-based model for Z, which is a exponential tilting of the Euro conventional non-informative prior distribution P0. And this energy-based model is defined by the negative energy function or objective function f of alpha z. and Z stands on a generator network defined by G of beta. So this is a generation error, and which is top-down, right? And this is a bottom-up network, which is often very small network. And X can be generated by Z through a top-down network parameterized by beta. And this direction is the conditional distribution or posterior distribution of Z given X. So again, this model captures the regularities or rules or constraints in the latent space, or it captures the objective or cost or value probabilistically in the latent space. And the sampling in the latent space can be very efficient and can mix very well. And in fact, we can also learn an inference model that directly generates Z given X, and we can generalize the VE framework to this type of model very easily. So I already showed you that the model can be used for image generation, which leads to very good FID scores. And in fact, perhaps a more interesting application is a text modeling or text generation. So here, the generator model become a autoregressive model instead of a purely top-down model. So this autoregressive model can be parameterized by any recurrent neural network. And here we can consider Z as a sort vector. So it is a thought about the whole sentence. And then you can see that it controls the generation of each token in this sentence. Suppose we have capital T tokens, and this is autoregressive model. And the thought vector Z actually controls the generation of each token in this sequence. And we can interpret this Z as a thought vector about the whole sentence. And here are some examples for generated sentence. And here we show the energy function or energy value over this short-run MCMC. And this method can generate high-quality sentences as measured by the perplexity or negative log likelihood or some other quantitative measures. And in fact, it can also be used for generating molecules or compounds. So here, each compound or molecule can be represented by a sequence called smells. It's a string. So we just treat this as a language model. And then this latent EBM, energy-based model, actually captures the chemical rules implicitly in a probabilistic way in the latent space. And again, this latent Z as a thought vector generates a whole string, which gave us this configuration of the molecule. And again, we evaluate the generation quality based on validity and novelty and uniqueness. And this method seems to be very promising. And we can also use the latent space EBM for anomaly detection, where we can use this joint density as an evaluation for whether an observation is an outlier or not. And it achieves quite impressive performance for anomaly detection. Another important application is the trajectory prediction. Suppose we want to predict the trajectories of pedestrians, multiple pedestrians. And here again, we can use a latent Z as a thought vector or a belief vector for the whole trajectory. So it generates the whole trajectory. And then we can treat this prediction problem as a inverse planning problem. So that is, we instead of learning a autoregressive model, very much like a policy network, we actually learn the value of those agents, those pedestrians. So this is encoded by this f of alpha z. So that is the negative energy function defined on z. This is like a value or a cost but it is defined on the whole trajectory through the latent belief vector. So this formulation, I think, is very important because it goes beyond the Markov decision process framework, which analyzes the modern reinforcement learning, deep reinforcement learning applications. In the sense that this model, first, it doesn't assume a Markovian dynamics. In fact, it put a probability density of distribution over the whole trajectory. It treats the whole trajectory as a whole thing that will be generated without this dynamic Markovian structure. And also, the value function is not a simple summation of stepwise cost. So this, I think, is a very useful generalization over this MDP framework, and it performed very well in terms of trajectory prediction. And this model can also be used for semi-supervised learning. As I mentioned, energy-based model is a generative classifier, but this time we built the classifier in the latent space. So that is, we now have a label. This label is like a class label, a categorical or one-hot vector. And this Z is a dense vector, and X is observed example, say an image or a sentence. And this time we have a latent space, energy-based model that couples this symbolic one-hot vector and this continuous dense vector. And then again, this X is generated by Z. So that is, given Z, then Y is independent of X. So Z is like an information bottleneck. In fact, this top-down model actually gave us a better or more natural interpretation of information bottleneck. And then the prior distribution is again a energy-based model, but the energy is in the form of a coupling between symbolic one-hot Y and continuous dense Z vector. And then this conditional distribution of X given Z continue to be a generation model or a RNN model for the text situation. And this P of alpha Y given Z is just a softmax classifier. So that is, we learn a classifier in the latent space, the regular softmax classifier in the latent space, where supposedly Z should extract all the information in X that is relevant to the classification, to the class label or category Y. And in fact, we can learn this model unsupervisedly. So that is, we don't need Y. We can sum out this Y, and we can continue to use this log likelihood to learn all those models. And we can also bring in the label data so that we can add the conditional log likelihood. So this is just cross entropy loss for the classification. Okay, so by joint maximization, we can then learn from both label data and unlabeled data. And in fact, this method achieve quite impressive performance for semi-supervised learning on text data and tabular data. And also it performs reasonably well on the image data. And we can also use this as a similar model for the controlled text generation. So again, X is a sentence text, and Z is a latent thought vector. But this time we also couple this with Y. Y may be, say, different topics and different emotions, sentiments, or different actions. Okay, and then we still have such a model so that this is a latent space energy-based model, and energy is a coupling between Y, symbolic Y, categorical Y, and dense continuous vector Z. And we can also learn a inference model to amortize or approximate the short-run MC sampling from the posterior distribution within the variational autoencoder framework. Okay, so we have all those elements, and we can learn the model in an unsupervised way or in semi-supervised setting. More importantly, so this is the likelihood, the elbow, the evidence lower bound in the VE framework. We can also add this term so that we can decompose this regularized objective function in those three terms. So one is a reconstruction for learning this generation model, and the other is the prior learning for learning this prior model, P alpha, the latent space energy-based prior model. And this term is quite interesting. This actually defines the information bottleneck. So that is by adding this term, we actually arrive at this information bottleneck in the sense that we want this Z to extract information from X, but only as far as it is relevant for predicting Y. So this is the information bottleneck. So that is, this quantity actually appears very naturally in this top-down model. And the top-down model is more natural for abstraction. So this Z is the abstraction of X for predicting this Y. And this model can be learned in unsupervised setting or supervised setting. So that, for example, in the unsupervised learning, we can actually discover the action and emotion labels in the daily dialogue, so that we can sample the actions and the corresponding sentences. For example, the action may be inform weather, or the action may be request the traffic, and then we can generate those utterances or sentences. And we can also generate the text in a very controlled way according to the sentiment. We can control the sentiment, and we can generate, say, positive or negative reviews using our model, because we have latent thought vector, which is generated by a energy-based model, and this thought vector controls the generation of the whole sentence. So I think now we arrive at the conclusion of this tutorial. Just as a summary, so in this tutorial, we present the following models and methods. So first, we present the data space EBM, the energy-based model in the data space, say in the image space or in the video space. And also, we studied the interaction of the EBM with the generative model. For example, we studied cooperative learning and divergence triangle learning for the joint training for energy-based model and the generative model, where the generative model serves as an approximated sampler. And we also studied the latent space EBM, where we move the energy-based model to the latent space, which seemed to be an even more natural home for all those MCMC calculations. And in fact, for the text data, this is discrete data, but you can still move to the latent space so that it is a continuous space. You can still use Lagrange dynamics for sampling. And finally, why is energy-based model useful? Hopefully, from this tutorial, you get some basic ideas why they are useful. But just to summarize, so first, it can be a very good density estimator, and also it can be very strong a synthesizer. So it can generate very realistic images, especially because on top of the generator in the cooperative training, there's also a refinement process guided by a learned energy function or objective function. And you can think of this energy function captures the soft objective or cost or value, or capture the soft regularization or rules or constraints. So here by soft, I mean probabilistically. So it's not deterministic, it's probabilistically. And also, perhaps more importantly, you can think of this energy-based model as a generative classifier. And then you can actually learn it from unlabeled data as a matter of contrastive self-supervised learning. For example, in this flow contrastive estimation, right, we use a noise contrastive estimation framework. So it actually unifies both this discriminative learning and generative learning. Okay, so this concludes our tutorial. I hope that you find this tutorial useful and helpful, and hopefully I will see you guys produce more interesting work along those directions. Thank you very much.